Okay, my friends, get ready for a little time machine going back 2.5 billion years, they're claiming. I say no. We will find out. I challenge their challenge, which is from a new study. So their challenge says the 2.5 billion year old time capsule rocks rewrite history. Again, I mean, you rewrite it every day now. Now we know everything. Tomorrow we're going to know it again. The next day we're going to know more. That's the way it works. But you have to examine what challenges, and I challenge. They say their study challenges mantle oxidation theory. I challenge their challenge. So let's see who wins the challenge. But I have to be able to be heard to be able to challenge. And I'm not able to challenge. I'm going to show you things in my microscope that'll challenge everything they say. And the chemistry, I mean, the whole 9 yards. I have everything to support everything that I'm saying. They have nothing but, well, I'm going to show you what they claim, and they claim this is really, it means nothing, but we're looking and we're thinking and we're really doing our job. Well, let me show you what I have to present. Then you can look and think and do your job. Until you look and see what I have to present, which is all scientifically backed by every possible way, DNA and CAT scans and specimens, and as I'm going to show you right now. If you can deny this, deny it. But test it. Don't tell me that I'm just an idiot. Because what I'm going to show you is undeniable. Absolutely undeniable. And as you will see, I have much to display, my friends. Okay, my friends, here it is again. 2.5 billion year old time capsule rock rewrites history. Now they're looking at this, and I'm going to explain to you exactly what they're seeing here, and I don't think they understand. Now it's a thin slice of ancient rock collected from this ridge near the North Pole under a microscope and seen under cross-polarized light. And this is what they see, and they're trying to interpret what they're seeing. And they're saying this is 2.5 billion years old, and all of this is a product of melted minerals. All right, so that's their stance. Okay, this is the 2.5 billion year old rock, and that is a lung. And I'm going to show this in extreme detail. And this right here in my microscope is also a lung that is not saturated in the ocean water, so it didn't turn all one color. This still has a lot of transition metals in it. Now I'm sort of free-handing this, so. But you can see all these little spots and all that. You see where it gets real shiny? I put a little water on there. Now, where it's real shiny is where it's cut, and that's all the mineralized portions. Where it's dull looking, that's where the blood is. The blood runs all through your lungs and absorbs all your oxygen and so forth. But you work with all these different transition metals. And the transition metals are what's in your blood. So let's get started. All right, let's start right off with the claims. This is the scientific interpretations and their insights into what might have happened. They're trying to explain this low oxidation level in this particular layer of rocks that they collected from the seafloor. Now, the team applied multiple models to their measurements. The models revealed that the low oxidation levels they measured in the samples could have been caused by melting under extremely hot conditions, deep in the earth. Well, that's what they're saying. Both lines of evidence back the interpretation. The rock's atypical properties, the totally crazy properties, represented a chemical signature from having melted deep in the earth during the Archean age, when the mantle could produce extremely high temperatures. How would they know that? They don't realize that these layers that they're seeing of rock were at one time biological. Let's see what it talks about the Archean. This is when they say this is possible that all this stuff happened. All right, you make your own assessment, but this is what they claim, is this all happened as a signature of the Archean era when the mantle could produce extremely high temperatures. Well, here is when the Archean era was. This is millions of years ago. This is 3,000 million years ago. That's 3 billion years ago. Now, this is before there was even oxygen, they say. And single-cell life came a little after that, and then water and all that stuff. No, this is just not true. I'm going to show you what they presented, and I'll show you what I can present, and I can tell you right now, it's not what they're telling you it is. I'll show you, and you make your own determination. Okay, this is how they date things. They're talking about the Archean area here. Right here. That's 3 billion years ago. All right, and that's best when they started getting photosynthesis. All right, way down here, you see this Ediacaran biota? That's not that. That's the Triassic era right here. This is the Triassic era, and that is not, you know, millions of years ago either. This is only 3,500 years ago all this stuff happened. They got this so far wrong, it's unbelievable. All right, this is their claim. This is one of their rocks. And they say the properties of these rocks show they likely date back to at least 2.5 billion years ago during the Archean eon. Further, the findings show the Earth's mantle has overall retained a stable oxidation state since this exact occurrence. Since these rocks formed, all of a sudden everything went stable, in contrast to what other geologists have previously theorized. They thought the oxidation state went up and down. All this. No, it's pretty stable except for this event, which wiped out virtually everything on Earth. This is not just a rock devoid of oxygen. I'll show you what that is. See, don't get confused. This Archean is 3,000 million years ago. These are millions of years ago. All right, so the Archean, what we're talking about, they're saying is 3,000 million years ago. That's 3 billion. They're talking about 500 million years ago is this Ediacaran biota. Everything I have is that from this era, and it's all on the top of the Earth. I just picked it up. It has nothing to do with it. They have everything so far wrong, it's unbelievable. Now I'm going to show you what they're talking about here is this all melted because they look at this and they say it's all melted because it crystallized in this form. Well, I can tell you why it's showing this. This is extremely thin cut. And what they're looking through here is different biology. Now let me show you. Alright, somewhere in this video, and I may have already shown you, but I don't think so yet, I'm going to show you an opal heart. And you're going to see how the separation of tissues takes on different colorations. That's what's going on here, and they are separated. It's not like this blue just mixes in with this block. They don't. You see these separation layers? Even this color of blue is not the same as that color of blue. There's all of these little lines separate the chemistry that's within the next block over. And these little lines are biological. They are not just cracks in the seams in a rock. This is biological. Now don't forget, this is what they're saying. They took very, very, very thin slices, and then they saw what's in here by these different colors to indicate different chemistry. And the blues and the reds and the pinks and all this, and then all of this, these little vasculature looking things. And these fluid-filled highways, they look like to me. What's going on with that? And all of that colored chemistry, what's going on with that? They think it melted and it recongealed and it fractured into all these different conglomerations of the same type of stuff, whatever the blue is and whatever this is and that. They're just all globbed together. And I understand why they're thinking that, but I don't believe that's true. All right, here's the deal. I've shown this a million times. These are all transition metals. You see how they have all these charges? They flow through the watery substance of your blood and your plasma and lymph, and they pick up and deliver things. They're with something that's called ligands. The metal is in the core, these metals, and they attach to all these little things, they hold on, they bring them down, drop them off, pick up a couple of something else, bring it back, flush it out. Boom, ba boom, ba boom, ba boom, ba boom, ba boom. That's how your blood just continuously does this. Now, so it has an affinity to pick things up based on these charges. So if you die, your blood is still in your body. And in the case of this boiling hot water flood, which created all these things I'm going to show you, and the ones that they think are 3.5 billion years, or however they think they are, 2.5 billion years. Anyway, these transition metals will invade primarily where there was blood, because blood is where all the transition metals are. Your blood is just literally saturated with all of these metals, and primarily iron. Now, so when you die, or when a creature dies, the blood is still in there. Now, if it get washed out, well, then the body tissue changes in one specific way, and depending upon whether it was cooked before all of the blood was drained out or not, or whether it was cooked with the blood still in it, how long it soaked, what the pH was, what the specific piece of material we're talking about was, how close to what type of an organ was it, because your organs in your body create different chemistry. I'm going to show you right now a heart, and you remember all these colors. And I said, I tell you, you see these charges? They will try to find a partner that wants 4, or wants 3, or wants 6, or wants 2, or to become stable. And then they'll lock in, but only if it's in the right conditions. Now, opals are the right conditions, because opals are nothing more than biology. Now, here's an opal that's a heart. Where did it go? Here it is, right here. That's a heart. Now, that's what they call a Yoa nut. And these are all over this particular area in Australia. Now, this heart was laying down on this side, was down. And I can tell that because of the colors of the transition metals are in here, which means they sink to the bottom. This is almost primarily red at the top, because that's the plasma. It doesn't have the weight of the transition metals. Now, so it's laying like this. All this blood in Australia, they have opals everywhere. So it's really like, I tell people, I say, as far as I'm concerned, Australia is like just one big gigantic scab. It's just a solid red scab. And all of the transition metals are everywhere. So in certain places they sunk in. Now, watch this. This is very, very unbelievably cool. We're looking at like the heartstrings. I don't know, let's call them the heartstrings, ventral walls, whatever you want to call them. And they have these little fibers coming down, and then they change as they get deeper into the heart. However, here the blue wants to be attached where you see these little strings and all that. And then all of a sudden, remember now, it's laying over like this. You see a little bit of green here instead of the blue. And then you look over here, you see there's green. Why is it green invaded where it should be blue? Because this wants to be blue, I believe. Now you see all the green here? This is a heart. And your heart is right in, bundled in with all your other organs. Now what was next to it? What created this chemistry? I don't know. But I would say that this heart was laying like this, and right next to it, right over here, was like the liver, or a kidney, or whatever it is. You have to look up the anatomy and see what's sitting next to there, and what type of transition metal would invade here. Because the other thing was here, and it's going to seep out its stuff like this. Transition metals, well, enzymes, it would have enzymes in it. Whatever it was, it would have enzymes in it. Enzymes break things down, reconstruct things. So it turned this into green, where it was normally be like this color here. This is over here. Boom. You see this? All right, don't forget now, this is going to be laying on top of that, and the whole thing's going to be like this. This color here, all these different little colors, the green must have been down a little bit low. You see, because you don't see all, well, you see it's pretty good green here. And some of the green is working its way in. But on this side, it's just solid green. Well, you know, it's pretty greened. And actually, it doesn't really look like it invaded too much of the blue fibers. The blue fibers definitely have an affinity for this particular blue, whatever it is, transition metal. So, you know, they're fascinating to look at how all that chemistry came in, and what it is the transition metal wanted to find somebody that had the exact right stuff to match together. Boom. Okay, it's me and you forever now. Okay, good. Boy, you're blue. That's okay. Yeah, blue works for me. Why not? And this one over here is green. Yeah, you're green. Who cares? It's just, yeah, it's amazing. And of course, that's the muscle area around the whole thing. It's hearts twist. All right, so then they go on to show these rocks, and they talk about being 2.5 billion years old in the Archean eon, and we're going to look at that in a second. I claim this is not, and I have rocks here that are almost identical to this, that formed not under the ocean, but here on Earth. And I will show you in my microscope in a second. All right, this is a sample of their 2.5 billion year old rock. You see all these little stripes and these green color? That's some form of transition metal that's invaded that, called nucleophilic invasion. And it's coated that circular vog with this particular product. Now, up here in my microscope is one I have here. Now, this stayed bloody, and it has all the same chemistry of a really good lung. And this is all the actual blood that surrounds the vugs. And this is where the transpiration happens. I don't know exactly how, but oxygen enters through these vugs. And the same thing here. Now, for this one, this was under the ocean for a bazillion years, and these are the exact same structures, and these little round holes, and this is the same as the, like up in here, the blood. But in the ocean, it just turned into, you know, I don't know what you call it now, but it's like a solid mudstone surrounding these crystallized forms. And what happens is inside the vugs of lungs, which I believe this was a lung, they had a lot of blood, and the blood starts to crystallize. And when it does, it takes on the most attractive transition metal. Let me show you. When I show you this should knock you out. All right, so don't forget this. I don't know why they can make these little stripes. I haven't figured that out. But they do the same. The lungs do that. That's just what they do. And this one here still has the bloody tinge to it versus the other one. Now, let me come down to, you see there? I don't know why they flap over like that, but this is where the blood is. You see all the bloody stuff running around in there? And there's all kinds of, there's another shot. Now that has a different tinge color to it than the other ones have, this pink look. But that's the same as, look at it carefully, you see it? It's basically the same as that. Now, why they make those stripes, I don't know, but they have them all over. All over they have them up here. If you look at it real carefully, you'll see there's stripes in all of these. That's very prominent. And this is where the blood runs in between all the different crystals. And this is some black, and that would have been where red blood was. It just comes out and then it fills in with silicates during this time frame. Now this here is a lung, and down in here was where, you know, air passed and blood and all that. Of course, there's another little alveoli here, and there's still a lot of the red blood tinged here. Now this is what happens when the crystals start to form. It's what's called a seed crystal. It gets locked in somewhere from the blood. I don't know how, to be honest with you, but you get a seed crystal. Then they start to grow. Now maybe that's why they're having these stripes. But normally they come out in like little round balls of crystals. And that's actually sort of the same thing. It's like a round ball of crystal, but on a different sort of idea than that, for sure. I don't know. All this stuff is very interesting to me. But I can tell you right now, this is all biology. This is not just something formed in the dirt. No, absolutely not. Everything I have shown you is biology, and so is the things they're showing. 2.5 billion years old, archaeon, and coming up with all kinds of explanations how it formed. They're just not right. And I'm going to show you this right here. Now, see this? I have one right in my shop. I have a ton of them, as a matter of fact. I got some in a microscope. I got one in a microscope. I'll show you right now from another lung. And it doesn't have the green in here, but it's got white. It's filled with white. And I'll show you. All right, we're going to get into the microscope, but don't forget, these are the little cavities, and this is the fabric, or the bloodyish area. I have one in the microscope right there. Now I have it highlighted in such a way that you can see the cavities. You see those are little holes that are the cavities. Alright, well I think you can see that. Now I have to turn the lights off to get down in here. And this is the top surface. And I'm not going down inside the lung. We're going to go down to where you see all these little holes and so forth. This is what they dug up off the bottom of the ocean. It's something that was like, I'll focus in on this a little better. But that's the underside of this lung tissue. And this is all lung tissue all the way over the top. And then where it gets to be fractured over here. And now we're going down into the lung. And this is the tissue that's in the lung. And these little circles of things. Now when I turn the lights off, we should be able to see a little better. Alright, you got to look real careful. You see these little dots and these little red dots all over here, and these little black dots? That's all part of the lung tissue. And the lung here these are all little holes, which are the cavities of the lung. And then coming down here is where we have the inside of the lung. It looks like this particular area was had a lot of dark blood, or black blood, which means it's a vein was entering this area and picking up oxygen or discharging carbon dioxide, whatever. But these are the little crystal balls that are inside the lungs. Now these don't have the little straight things across like these do, but they're basically the same thing. Now I think I have other shots of that. Yeah, all right, see this here? They're all over the place. And then you see this running through there? That's a little vein or an artery or some blood vessel. These are little blood vessels running through. And they're going to be blood vessels in there. That's just the way it works. And this might be some of the blackish blood, but I can see, if you look real careful and you can see the little red blood spots all over the place. There was red blood in here at one time. And they took it off the ocean floor. So there was a lot of washout, let's put it that way. Here's another shot of what they took up off the ocean floor. Now these little spots here, these are basically all the same as what I'm showing you in the lung I have here. And I can show you the outside surface, which I think I have, which is up here. And then we go down inside, and you're down into here, and we go even a little deeper. We can go all the way right down into the center. And it looks like all these little cavities play a part in the respiration. So you don't just have a few holes. There's a bazillion holes in there, everywhere. Everywhere. So this is the lung I have here on my microscope. This is where the blood flows as a little channel. Of course, it has all the little things. It is exactly, basically identical to that. There's blood flowing through that. There has to be little passageways where the blood flows. But then there's all of this oxygen intake in a lung, and I mean there is a million holes in there. I was very surprised at how many holes. I always thought there was, well, here, let me show you what, I have a lung here. Well, here's the lung right here that we're looking at. And that they're down inside, we're looking at it. So I always thought that these are all the holes that are in the lung, but no. Inside that black stuff there is thousands and thousands of tiny little holes. So it's not just these. I have another one here, there's a lung here. All right, so the scaffolding, that's fine. But all that, those are just big main entry points. And then they branch off of that into all of this tissue is just nothing but Swiss cheese. I mean, it's just a bazillion holes in there. And I'm going to try to put this back in and see if you can see some of the, if you look right there, I'll put this in. You can see, I mean, it's just riddled with holes. And of course, the outside has what they call a pleura, and that expands and goes like this all the time. And these are where the bigger alveoli are. And then below that, you see the red. That's where the red bloody stuff is. Below that is your actual lung tissue. And like I say, a lot of holes. I have lungs like, I have dozens and dozens and dozens of them. All kinds of, and I have one that's DNA tested. I have some that I don't know what kind of animal it's from. That's a lung. And that right there is the lock. They all have a little latch on the bottom. And that lock is right there, and it locked that lung in. Now, this one here, the latch, which is like that over here, it stayed with whatever it was latched to. It ripped right off of there. It's supposed to be here. And it comes up right to here, and instead of staying with the lung, it ripped off. This stayed with the lung. They usually stay with the lung. So that's kind of unusual. All right, I'm going to freehand this. I got it in the microscope. Every one of these little tiny holes is leading somewhere and the blood is leading down into it, or the oxygen or whatever. But if you get close enough, this microscope is not that good. But you would see there's a bazillion little holes in these lungs. And then they end up feeding out into these bigger holes, and there must be a network of them going around, and then all of a sudden they pour into the big chambers. Like this is the other heart, the other lung I have here. And here's the big chamber. You see way down in there, it just pumps oxygen everywhere. But they all have to collect somewhere in one big chamber. It's just like a ball of Swiss cheese. Okay, I know I showed you the opal heart. I'm almost 100% sure. Now, when they cut these flat like this and they look through this, they're seeing all these different transition metals, and that's what happens. I showed you what the transition metals are, and here they are, and they have attracted themselves to where they feel stable, and the tissues are separated in layers of different tissue, just as they are in where I was showing you before here. Hold on one second. Okay, I'm going to pretty much close it up at this. We're seeing they invade different types of tissues. So you will see these separations just as you're seeing them here. And that's precisely what they have seen in what they're looking at here. Now, it's just the same thing. It's all separated out in an extremely thin film. So this is blood vessels, or I think probably lymph nodes, lymph ducts, because there's so many of them. And they are, I don't know what the scale of this is, but lymph ducts are just as tiny as they can be. And that's what they look like here to me. Although this may be like an artery or a vein or something like that. But these little tiny bitty ones, I would say, are probably lymph ducts. I'd have to see what the scale of the size is. But all that, it's just what it is. And, you know, I have a heart here. You see that heart? That's a crystal. Well, here it is right here. That's the aorta, or you know, that's the main tubing, I believe, the aorta. And there's some blood in here. And that's the ventricle wall right there that separates the two. Now, this would have almost always broken off right there. They just break right off. You don't get the top part of the plumbing. This is just, for some reason, it didn't break off. They usually break off right there, right around here, and it just goes. And then you get down to where it's almost flat, where the valves are. This was from a long time ago. I think this is a lung, but I got to be honest with you, I'm not 100% sure. But they do take on these transition metals in the right conditions. You see that? That's a piece of meat. That literally is a piece of meat. And if I put a tiny little bit of water on here, it just immediately takes back the red color of meat. And that little flap right there is the attachment that attaches this piece of meat, whatever that was, to whatever it locks into, to lock into the body. They all have a tab on them. Wherever there's a chunk of meat meets something else, it has one of those little triangular tabs. I think I showed you the lung here. You see the lung? That lung has a triangular tab right there. That's exactly like that. This lung attached. This is a piece of meat, but they all have the attachment. This one broke off. That one had the attachment here, but it broke off and stayed with whatever it was attached to. I've got a lot of these. They'll have the same thing. They'll have that attachment. Anyway, I suppose I'm going to leave it at that for today. But if they're saying this is 3.5 million or 3.5 billion years old, that's not that. No, it's not. That's the little blood vessel running through there. They just don't understand what they're seeing. And I showed you what mine is. This here with all, whoops, where is it? With these little lines in here. I thought that was really cool. Where is it? This one here. You see what the little lines in there? And I have basically the same thing, only mine transitioned into the bloody pinkish. This, for some reason, was where maybe it was a gallbladder or something right in that area. But mine actually transitioned into, it has the little lines in here and all that stuff, but it's just blood. And this is actually blood. All that powdery brown stuff, that is actually blood that's filtering through the heart, through the lung. This is so far off, it's absolutely phenomenal. Every single thing that I'm showing you here, I just picked up off the ground. It's not buried 500 million years ago. No. And this is that Edicarobiota. They know my stuff is right. They know my stuff is real. I have my stuff DNA tested. I have my stuff CAT scanned. I present it to everybody. They just want to make up these things so they can go get grant money and go get money from NASA and everybody else. It was exactly what they did. And it was exactly what my research was into the mud fossils. And that's how they preserved. And they say this Edicarobiota is exceptional preservation of soft-bodied creatures. Exceptional. And that was Yale, after I had already presented my stuff to him a year or more than that earlier. And this is exceptional. I mean, the goose, that's a goose, and feathers and everything. See the feathers up there? I still can't find out what kind of it's a waterfowl of some sort. There's his little beak hole, and there's his eye, and you can see his neck is here. See it in the shadows? And that's where the artery is. This side is flat. They all died in the flood. And that was the Triassic, the red bed, gray clay, and black cap. Just remember that. Red bed was where all the flesh boiled off, and you had the red bed, it's just mud. Then you got gray clay above that, which is all the marl, that's the bones and the trees and all that other stuff on top of the fleshy stuff that goes quick. So then that's that gray layer, and sometimes it's greenish. And then above that is the black cap, all the fallout from the explosions and volcanoes and burning and all that, because we were almost hit by Venus. Many times gone over this, many times, and it's undeniable. So we are now being misled by the ones we trusted to teach. That's not a good situation to be in, not at all. So I'm going to leave you with that, and I think we have to just confront this and just stop and say, stop doing this to us. Stop telling us lies and forcing us to repeat that, and paying you to force us to say what you tell us to say, or you tell everybody we're stupid because we can't repeat what you told us to say, although we know it's wrong. I mean, they know it's wrong. There's nobody on the face of the planet right now that can deny the things that I have shown. Zero. And instead of confronting it and saying, here's why you're wrong, Roger, they are silent, and I'm talking dead silence. All right, so if you don't confront them, they are just going to keep doing what they've been doing to us for many years, which is just taking advantage for their own personal gain, not to teach you anything. And if you think you're being taught, all I can say is good for you. So I am going to leave it at that. Once again, we got to change the way we're thinking. We just got to change the way. We got to have an open forum discussion. If I can't be seen or heard by anybody anywhere, and I can't, they won't let me publish. They won't respond. Everything is. If they would respond, then I could respond. That'd be fine. But I have never had a single one of them would allow me to discuss anything with them, because all of this stuff basically destroys what they've been telling us. Even about Jupiter, I know about Jupiter. There's a great red spot's not just there from a storm. This thing's swirling through, and it's a bump. And I'm just not going to go through this anymore. It's just insane to have to keep doing this over and over and over and over and over again. But I will, until we get some satisfaction from the academics who have destroyed so many lives. All right, you hear me? They have destroyed lives. All right, there's people living in their cars right now, can't pay their student debt. They want us to pay the student debt because they've been taken advantage of. I say the colleges should pay. And Yale should be right at the front of the list. They should be giving up. I was saying 150 million. I think 500 million would be more like it, where we could start a school which was a truthful school, something honest. I submitted all this stuff to Yale years and years ago, and then they put out their own paper, which is basically the same thing I put out, and then they twisted a little bit so it made it sound like it really wasn't very meaningful. No, very, very meaningful, and it is our history. It's our everything. It's everything. And it's been denied by the people we trusted. All right, so I'm going to leave it at that. You do what you think is right. I'm doing what I think is right. All right, I love you all.